I think now we can start for this session, multi-threading. So from right now, we will go to parallel programming. Therefore, the first part of today's talk is about introduction to parallel computing, so that you will have some feeling or high-level overview about parallel computing. And then we will introduce the first part, task-based multi-threading in Julia, which is the intrinsic parallelization for multi-threading in Julia. Let's say the basic intrinsic way to do multi-threading. And in order to make this concept easier to understand, we have this Hello World example, but not like very naive Hello World, but with multi-threading. In order to put this multi-threading into more practical or more realistic applications, here we have a simple case study for the computation of the Mandelbrot set. And then we will introduce the so-called race conditions, which is a very common mistake that can happen for multi-threading. And then we introduce the second way, maybe slightly easier or maybe straightforward for doing multi-threading in Julia. So by using Julia, at least you have two different ways to do multi-threading to utilize all the CPU cores in one single compute node. So you have the choices to pick the one that you can benefit the most for your own research. And then a very short summary for this part. Yeah, without any delay, I think we are all here. Let's move on to introduction to parallel computing. So I think you are here because you want to do parallel computing using the HPC system. And the first question would be, what's the meaning of parallel computing? Some of you may think maybe I'm using multiple CPU cores, it's parallel computing. Some of you may think, no, it's not enough. I want to use multiple compute nodes, it's parallel computing. But actually, parallel computing has a more general concept, just to use the power of multiple compute units. Compute units here is a general concept. It can be CPU cores, CPU sockets, or whatever, simultaneously, so that you achieve the so-called parallelization. If you look at the architecture of a cluster system from the fine level means this is a node, a single node, with two CPU sockets, as you can see. Believe it or not, even for a single socket, you already have some parallelization inside. So basically, as introduced by Alex this morning, even in a single CPU core, you can utilize the so-called vectorization or SIMD or similar terms to take advantage of the so-called instruction level parallelism. Yeah, maybe you never realize it, but you are already doing parallel computing, even for a single CPU core, covered by Alex for this morning. And then a major task for this part is to do multi-threading so that you can utilize multiple CPU cores or multiple CPU sockets, as you can see in this photo, two CPU sockets to achieve parallel computing. However, this approach or this parallelization is limited in a single compute node. And for someone who is really ambitious, want to use the entire, for example, the entire Noctua 2 cluster system, or use the entire cluster system for your parallelization, Alex will talk about it, the MPI parallelization, tomorrow morning. But this afternoon, we will focus on this part, this level of parallelization, multi-threading inside a single compute node. You may have a question why parallel computing is so important. We can rely on the increased CPU frequency, right? Today, the CPU frequency is 3 gigahertz, maybe tomorrow 5 gigahertz, maybe the day after tomorrow 10 gigahertz. It's possible, but actually this is not really possible. Here on the left side, this is the development of the processors in the last 50 years from 1970s. As you can see, there is a dramatic change around 2005. So if we look at this plot, the number of the transistors increases roughly without any problem. And the single thread performance or single core performance for a processor looks not really great, but still increase. But one thing you may notice very clearly is the frequency of the processors. Let's say from 2005 until now, roughly 20 years, the frequency of a CPU is roughly 3 gigahertz or 4 gigahertz, maybe in the future 5 gigahertz, but no big change. What has changed a lot is the number of the CPU cores, those black dots or those black plots. As you can see, before 2005, normally one socket, one CPU core, but afterwards, more and more CPU cores are included. To give you a more concrete example is the HPC systems at PC2. So the Noctua 1 system was built in 2018, just a few years ago. At that time, the Intel CPU has 20 cores per socket, which means if you buy a CPU, it has 20 cores. So basically, one compute node, there are already 40 CPU cores you can utilize to parallelize your application. This sounds great, but a few years later, Noctua 2 was built, and for AMD CPU, it has 64 cores per socket. As you can see nowadays, in one compute node in Noctua 2, it has 128 CPU cores. This is fantastic. But what is more fantastic is this year, of course, Autos from PC2, for one CPU socket, it has almost 100 CPU cores, as you can see, 96 CPU cores. If you are using one single CPU socket, you are able to utilize roughly 100 CPU cores. This is a little bit unbelievable in a few years ago. And for one compute node, the user will have, let's say, roughly 200 CPU cores. This is a great power of parallelization, even for a single compute node. So that is why the so-called parallelization or multi-threading in this content is important and relevant for your application. So next, we need to dive into the so-called topology of those 100 or even more CPU cores. This sounds quite a lot, yes. So the topology of those 100 CPU cores is not like simple CPU core 1, 2, 3, 4. Yeah, it's not like that. There are some designs to make the performance to have the best for your calculation. And fortunately for Julia, there is a very good ecosystem. You can use the so-called HWLOC.Julia. This stands for the hardware, HW hardware locality this is a Julia package you can use to visualize the topology of those, I don't know, 100 CPU cores. And for visualization, there are two ways. One is to visualize like this graphically. One is to visualize in a text form. So to use this package, very easy, like we started in the beginning of the course, just using HW hardware locality, use this. And then if you want to know how many CPU cores are there for the current compute node, you just run number of physical cores. You will see it's 128 because this is a compute node, one compute node in Noctua 2. So that is why it's 128. And to get more details, you can use this graphical way for visualization. For example, the upper part, it is one single CPU socket. The lower part is another single CPU socket. And for more details, you can also plot to take a look at the text form. For example, one compute node and two package. Package means socket, two sockets, and then with different groups or NUMA domains and so on. So this is not, let's say, as simple as we might imagine, like a simple hardware architecture from 1 to 100. So therefore, we have this course to make you get more familiar with how to use all those cores by multi-threading for your own work. And Julia supports different levels of parallelization. And today I will talk about multi-threading. And tomorrow, Alex will talk about distributed computing. Okay, let's go. Task-based multi-threading in Julia. Before we really touch the Julia syntax for multi-threading, I can promise you the multi-threading syntax in Julia is very, very simple. Just one macro. Yeah, if I just talk one macro and then 5 minutes, the course is done. So let me give you more high-level concept about what are the threads. So first is the concept of a process. So a process is, you can think about it as a computer application is running. For example, if you are using Linux, you can use htop or top to take a look the processes. And I think maybe most of you are using Windows. You have this task manager and the listed, running applications. You can think of them as processes. And one process is like a big container, as you can see here. It can contain one or more threads. And each thread, they have their own dedicated content. This may be more friendly for computer scientists, but for most of you, those are just like their local resources for one thread. Here in this graph, I'm showing you one single process which contains 4 threads. And in addition to their local, their private resources, they also share the so-called heap, as mentioned briefly in the morning by Alex. So as you can see, every single thread, they are able to access this heap. So this may create some problem that I am going to mention later on in this part. Yeah, this access to the shared memory to this heap. But maybe you can simply imagine that if there is a shared resources, and it is highly possible that those 4 different threads may compete with each other. And then there may something unexpected may happen because they are competing with each other by themselves. And then Julia multi-threading was developed several years ago. And the basic concept is the so-called task-based parallelization model to leverage the so-called multi-threading by using multiple CPU cores. Here is for the purpose of illustration. I have six tasks. A task in Julia is, let's say, independent workload that can be computed independently. Like you can see here, 6 different tasks. And then on the other side, you have the so-called threads. And those threads has 4 threads, and those threads can execute those tasks, let's say, in a dynamic manner. And to determine which task will be executed by which thread at which time is fully determined by the dynamic scheduler. Therefore, it's not a problem that we have more tasks, but less threads. It's not a problem because all the arrangement or the management is managed by the dynamic scheduler. And then the thread pool allows the concurrent execution of those different tasks. So this is a very high level, let's say, overview about it. And this is to show you how this is scheduled. So first, you have a task pool, which may be some calculations. And then from the hardware level, this is the software level. From the hardware level, you may have different CPU cores and different threads. And then there is a scheduler determining which task will be executed on by using which threads on which CPU core and so on. So basically, it's fully dynamic, but for you, I would like to say this is most challenging part for doing multi-threading. You need to make sure that the code correctness is independent with respect to the order of the execution of those tasks. This is sometimes very challenging. And here I try to give you a more concrete example. For example, you have an input vector which contains 6 elements. And then you have 3 tasks. The first task is to calculate the average of those 6 elements. And the second task can be very different. For example, to calculate the norm of this input vector. And you may have more tasks than the available threads. It's not a problem. It's not a problem. There's no, one-to-one fix for this. And you want to calculate the sum of this. And on the other hand, you may have only 2 threads. And then the dynamic scheduler will determine which task will be scheduled to be executed. Here, let's say at this time slot, those 2 tasks, average and norm, will be executed. And maybe in the next time slice, the sum will be scheduled to be executed. But the most challenging part for you as a programmer is to make sure that the final result is always correct, independent of the order which task will be executed. Okay, that's all for the high-level part. Now, let's dive into multi-threaded Hello World by using Spawn, which is task-based parallelization. To use multi-threading, first you need to, let's say, to use the base library. The base library is the core part of Julia, the base part of threads, and then to import Spawn, thread ID, and the number of thread. Here, after import those macros and functions, I create a variable which is 2 times the number of the threads. And then we have this function hello spawn. This is unlike a normal hello world function because this is multi-threading. We have a for loop so that we can take advantage of multi-threading for this for loop. Without multi-threading, as you can guess, the for loop will print I equals 1 hello world from, just sequentially, always from 1 to n. But you can parallelize this very simple example by prefix this spawn in front of this print L. So what spawn does is create a task, This is a task to print something here, to create a task and then dynamically schedule it to run on the available threads. As you can see, this is very simple, just one macro. But after spawn the task, synchronization is needed to make sure that all the tasks in the end of the day, they will come together. You can think of this process like what we have during lunch, right? Before we start the lunch, we have this spawn. Yes, we spawn ourselves to Mensa. You may pick, I don't know, Wurst or Schweinsschnitzel, whatever. You can do whatever you want. And of course, out of order. There's no regulation that, okay, the people who eat Schweinsschnitzel eat first, the people who take other eat later. There's no such a regulation. You can do whatever you want. But after lunch break, in the end, we need to synchronize, which means in the end of the day, if we think of ourselves as threads, we need to get together into this room. So it is super, super simple by doing multi-threading in Julia. So maybe I can close the course right now. Only 2 macros. One is spawn, one is synchronization. It's done. But actually not really so simple. We also need to know the thread ID. For example, what you would like to order. And also the number of the threads, number of the participants, go to the Mensa and so on. So this is the concept I would like to say. If you, please. Sorry? Yes, because I want to show you something that will be executed out of order. Yeah, to show you. This is just to try to make the concept of out of order execution more visible, let's say. So there's no particular purpose to multiply it by 2. And to execute this code by using multi-threading, for example, if you have 4 CPU cores, and then you can use the option -T4 or --threads 4, or set the Julia environment variable Julia number of threads equals 4 to use multi-threading to execute this code. Yes, as you just mentioned, I multiply this by 2 because I want to make the output messy. As you can see, if I do not multiply it by 2, you will see only 4 lines. If I make it multiplied by 2, you will see more lines. And pay attention, those are just the possible outcomes. Possible outcomes means those outcomes may change, depends on your execution. Every time it will be changed. So actually, during the lunch break, I copy paste. You can also simply copy and paste this into, as you can see, Jupyter Lab. If I run this, now you see I is 1 to 8, 4, and 1 to, and here, 1 to 2 to whatever. But if you execute this again, you see this changes. it's not definite. You know, the results is not really determined. But the most important part is the code correctness must not rely on this dynamic scheduling. Yeah, this is the most challenging part. Okay, I think, yes, please. Some thread will walk around in the campus and not coming to this room if there's no synchronization. Yes, for very simple example, you may not notice. For example, if we only have 4 participants, maybe we already have some agreement, we will come here. But if we have so many people, I'm not sure someone may be enjoying the sunshine not coming here. So that is why synchronization is important. It is needed. And the error may not shown for some simple example, but this is definitely needed. Yes?
So that means here it should show out of order, but you don't get any error. So I mean, so in the next slide, you should show that thread 2 out of 4. I mean, my understanding it should be error, right? Not so there it's running at some of them thread 3. Basically, there's no thread 3 available, right? Because the number of threads.
Yes. Yes, I fully understand. That is why I spending so much time on those non-Julia concept. As I said, the number of the tasks can be whatever number you want, and the number of the threads can be whatever the number of threads you want, and the scheduling is also dynamic. This thread, let's say thread 3 or whatever, may exist, but the dynamic scheduler may never ever schedule a task onto this thread. Yeah, this sounds strange, but this may happen because this is a so-called dynamic. And maybe the dynamic scheduler like thread 2 and schedule everything to thread 2. That is also possible. In this, we have 4. Which example? There's no, the number of the threads, the total number of the threads is always 4.
I think this question is for after multiplication or before multiplication.
This n is the number of these loops. I make this n larger only to make the out of order execution more visible, you know, to make this messy, even more messy, so that you can see that the output is really dynamic. Yeah, it's yeah, the number of the threads is always 4. This is definite. I can promise. Number of threads is always 4. If you, if you specify to use 4 threads, the number of the threads is always 4. But the thread ID may change dynamically. And also the order of the output, as you can see, the order is 2, 4, 3, 5, 7. And this order is 1, 5, 6. You know, this can change to whatever, you know, the dynamic scheduler want. As you can see, this is a very messy situation, But the most challenging part for you as a developer is to make sure the code is correct. Yeah, this is a very challenging part. I hope this is clear. Or maybe we can talk privately afterwards. Yeah, it's not a problem. I know it's very confusing. Everything is messy, but in the end of the day, the result is correct. Yeah, this is unbelievable, but it happened. Yeah, in order to make this talk a little bit shorter, I would like to know how many of you has already know the so-called Mandelbrot set. Okay, great. And then I will just mention this very briefly. So Mandelbrot set is a set of images, some pixels around here, and one just do this iteration, and to make sure that for some pixels, it is if it is always converged like this. First iteration is this value, and after 4,000 iterations, the value does not change. And then this complex number belongs to the so-called Mandelbrot, those Mandelbrot set, this black area in this region. So just do this calculation. And the goal of this Mandelbrot calculation is to generate, for example, this image. And as you all know, to generate this image, one needs to calculate one pixel first, yeah, in order to generate the entire image. Therefore, to calculate the one pixel, one can have this function to calculate the pixel starting from one input complex number and then do this iteration. Yeah, this 4i equals 1 to the number of the iterations. Here, I set this number of the iterations to be 4,000 or 4K. You know, for computer, we cannot do it infinitely. So we just set a number, the maximum number of iterations. If during the whole iteration, the value does not diverge, and then we say, okay, this is value in the Mandelbrot set. So that is why here you have this for loop. But if this value diverges, and then it will return immediately to return the reminder of something. Let's just make it simple reminder of something which represent the color of this pixel. So very simple here, to compute one pixel, you have a for loop. And if this for loop gives you a converged value, this belongs to this black area, the so-called Mandelbrot set. Otherwise, it belongs to some other area. So this is how to calculate the pixel. And here, maybe you notice the inline macro. So inline macro is a small trick to make your Julia code faster, because if this function is inlined inside a large function, and then some additional optimization may take place. So this is the trick why here you see this inline. I hope this function, the meaning of this function is clear. You needn't to think about more details, but from a high level, first, you calculate one pixel. And the next step is, of course, to calculate one column, right? You have you calculate one pixel and then you calculate one column. And the function to calculate one column is to first identify the x value and then go through the number of the rows from 1 to n. N is the dimension. And but anyway, you needn't to pay attention to the details of the code. Just from high level, you calculate one column. And in the end of the day, you calculate the entire image, right? This level is very clear. You compute this image by call this function, calculate image serial, of course, because this is a single-threaded code. And then you have the very outside loop, which will go through all the columns from column 1 to column n. You see the concept is very simple. And you can just copy and paste those codes and then to let it run, I don't know, your laptop or Noctua 2. For Noctua 2, if the dimension of this, if this is a 1K times 1K image, you will have the runtime of, let's say, 2.1 second. This is the single-threaded implementation. Yes, because most of the materials are from the so-called HPC from Professor Plaza. For computer scientists, they would like to learn more about the so-called, if this computation is memory bound, you can forget about the other text. If this calculation is memory bound or the so-called compute bound. Because from computer science, if this calculation is compute bound, this means in theory, if you have more and more CPU cores, you can improve the performance continuously because it's bound by the computation capability. Otherwise, if the calculation is bound by memory, from the memory transfer, and then by using more and more CPU cores, you get nothing because the bottleneck is the memory. Here we are lucky, this is compute bound, which means if we are using more and more CPU cores, we will have better and better performance. And maybe let me ask you a very simple question, even without a knowledge of Julia. As I said before, the image is gone, but anyway, there are 3 levels of for loops. The lowest level, the innermost level, is a for loop for one single pixel, right? This is the innermost for loop. And then the loop is to calculate one column, right? To calculate this one column from row 1 to row 2, row 3, and continues. And the last step is to compute the entire image from column 1 to column 2 to column 3 to column 4. Even without Julia knowledge, maybe would you like to just make a guess which loop should be parallelized? Or maybe just throw some random number. Yes, please.
Say the column calculation and the complete image calculation.
The complete.
So both the second and the third.
Okay.
Because the computing 1 pixel is independent to 1 pixel.
Mm-hmm.
So we can do that over the whole image in whatever order we want.
Yes. Okay, great. Maybe some other answers or. Okay, please. Okay, great to hear. Please, lady first. Yes. Yes. Okay, nice. You, please. Okay, yeah, also good opinion. Yeah, but anyway, everything is great. Yeah. So the key is to divide. Sorry, I blocked this. Is to divide this calculation of the entire image into, let's say, column-wise, and then let each thread to calculate each column. I know some of you may against this idea, but let me explain. So in this way, you only need to insert what we have talked about, the synchronization and span into the outermost column loop, for this image, and then the parallelization is done. The parallelization is really done. And for the so-called task, it is the calculation of this column. As you can see here, there are some threads to calculate this individual column. And then in the end, all those calculations must be synchronized in order to produce the final image. So I hope this makes sense. And if you do not believe me, there are some rule of thumb to achieve good performance. The first rule of thumb is to have a reasonable number of tasks, apparently to avoid millions of tasks. Do not press too much to the CPU, avoid millions of tasks. This is not good, to schedule millions of tasks. This will be a huge overhead for the operating systems and so on. And the second is also very clear, I think maybe for some of you, to avoid little work for a task. For example, just do multiply and add, and then this is a task. No, this makes no sense. You need to give enough work, enough calculation, for example, enough work for computing this column to one task, and then have, 1,000 tasks. This makes sense. Instead of, let's say, give 1 million tasks, and one task does almost nothing. This does not make sense. So this is a very high-level rationalization for multi-threading. And the syntax for Julia is done, let's say. It's really done. Only two syntax. One is synchronized, one is spawn. And then, as you can see, let's look at the performance. This is a while time. With one single thread, it's roughly 2.1 seconds. And up to 64 threads, as you can see, this is very nice. The runtime decreases. And if we look at the speed up, let's say with one thread, the speed up is 1. And then with 2 threads, the speed up is 2. With 4 threads, speed up is 4 until 8. And then you will see the problem. With 16 threads, the speed up is only 15. With 32, the speed up is 28. With 64, the speed up is roughly 52. This is, let's say, also a very challenging part, because with the increased number of the CPU cores, the speed up increases, but the so-called parallel efficiency, which means how could one realize the parallelization more efficiently, start to decrease. But what I would like to promise is that is not your fault. That is not your fault. That is the problem of the so-called, let's say, CPU frequency. Because for modern CPUs, if you are using one CPU core, you may get higher frequency. Because one CPU core, if you are really using one CPU core, you will have higher frequency because of energy consumption, and heat dissipation and so on. But with more and more CPU cores are busy in order to reduce the generated heat. I think many of you know the cooling system. In order to reduce the generated heat, the frequency of a CPU core, for example, for one entire socket may be reduced slightly. That is why, in the end of the day, for example, here, when 64 CPU cores are running, maybe only maybe 3 gigahertz. But if you are using only one single CPU core, this core may run at 4 gigahertz. That is why here the parallelization is not really perfect, but this is already very good. So as you can see, with less CPU cores, you have perfect linear speed up, and then problems happen because of the reduced CPU frequency. Okay, and then we move to the very common mistake created by, this messy, access dynamic management of the threads, this will generate the very common mistake, the so-called race condition, which means different threads, they try to have a race to compete with each other. And then there's a problem. So to make this race condition more clear for you, I'd like to use a very simple example, the Leibniz series, to calculate the value of pi. I think most of you knows what is Leibniz series, right? Or yeah, and then there's no introduction about it. And then just a very simple serial implementation for the Leibniz series. And once again, this is compute bound. This is very nice because with the increased number of the CPU cores, we may have increased the number of the performance. And as you can see, in order to calculate this series, let's say we just use n equals 1 million, which means we just calculate 1 million terms. Maybe you may say 1 million term is not really needed, but here 1 million term is only to show, is for the purpose of doing parallel computation. In reality, maybe 10 terms is enough, but here we just set 1 million terms. And in the to start, we set initial value, the sum equals 1, which is this 1. The initial value is 1. And then we started to go through this 1 million terms, do very little calculation here. As you can see, just if this is even number or not, it's 1 or minus 1, and do some division and then finish. Very little calculation for each term, but one need to go through 1 million terms. And then in the end, return 4 times the sum of the term. So with one CPU core from Noctua 2, you have correct value of pi, which is 3 point whatever. And then the while time is 1.6 millisecond. Yeah, 1.6 millisecond. And yes, now we all know the syntax for multi-threading in Julia. One is synchronization, one is spawn. Let's just put synchronization there and spawn for the calculation of the one of those terms. Let's just do that if this works. Here is the so-called naive implementation, just using synchronization and spawn. Yes, this is a naive thing. Put synchronization here, put spawn here. And you will see that there are 2 major problems. The first major problem is performance. Yeah, I said one may, the programmer may not realize that he or she has spawned 1 million tasks, but here it happens because we want to calculate 1 million terms. And here, as you can see, n is 1 million, yeah, even more than 1 million. And here, one can easily spawn more than 1 million tasks. That is really bad for the performance. And the second problem, like I mentioned, let's say 10 minutes ago, is little computation for each task. If you look at this task is inside this begin and end block, right? This task does, I would like to say nothing. Just the division, this task does nothing. So those 2 major problems are here. One is 1 million tasks. One is one task does nothing. But those are performance problem. One serious correctness problem is the so-called race condition. Race condition means here S is actually started from outside of this multi-threading region. And here, as you can see, those 1 million threads, they are free to access this or to make changes to this, let's call it global variable S, right? But as I mentioned before, there's no guarantee that thread 1 will be executed first and thread 2 will be executed second. It's fully dynamic, out of order, it's messy, it's completely out of order. And in the end of the day, because this is will be executed in whatever order the operating system, the machine want. And in the end, you will have a very wrong result for the calculation of the pi. And if the result is wrong, there's no meaning to measure the performance, right? And then this is a so-called race condition. So basically, several tasks or threads, they try to update the shared variable in the heap. Maybe you mentioned, you remember the very first graph, the heap in the very top, every thread can access, and then it will generate unpredictable behavior. And this will happen for some problems to calculate global values, like here, global value. And each thread will add their local value to the global value out of order. Here is a small graph. I'm not going to dive into details because of the time reason. And Julia offers two solutions. One is atomic operations, as you may think about, atomic, which means to do operation at one single atomic value so that one can get rid of the influence of other threads. One is the so-called lock and unlock. This is like if something lock this variable, and then no other threads will access this variable and then can get rid of this data race. But for this course, we will not touch lock and unlock, just focus on the so-called atomic operations. Okay, atomic operations. So atomic operations is a thread safe way to get rid of the data race. This is like operating on a single value to treat it atomically. And therefore, the code or the data that will be updated will be serialized, because only one operation can be executed in one time slice. That is why it will be serialized, and this will have bad impact for the performance. And but anyway, for some operations, the compiler may take advantage of some CPU instructions to make this operation efficient. For Julia, you can create the so-called atomic object by using this threads dot atomic followed by the type of this variable to create a special atomic object, so that this object or this variable will only be updated by a single thread. And the type of this atomic object is limited to basic types. For example, Boolean or integer or floating point numbers, not applicable to structures. And the syntax is slightly lengthy, but in such a way, you can create an atomic variable for in Julia, so that you have a thread safe code. For atomic operations, it's also somehow limited to simple add, but with more complicated syntax, this lengthy syntax to do atomic add operation, or do atomic subtract operation, or to find the maximum, and so on. I think for this detailed Julia syntax, you can look at the documentation. And for our problem, the solution is here, as you can see. In order to solve this problem, we need to make sure that the variable S, this global variable, is thread safe. Therefore, we make it the so-called atomic variable, which has a type of double precision or float 64 with an initial value of 1. And then we use the syntax, sync, and spawn we learned previously, and then do the add for the many different terms. Instead of this normal add, just the plus sign, we use this atomic add to do the accumulation of the sum of those terms. And then we return the result, which is 4 times S. S, but followed by square bracket, because this S is not a simple scalar. This is an atomic, let's say, atomic variable. That is why the syntax is a little bit weird. But anyway, here you can look at the results. Using one thread or whatever number of the threads, the value of pi is always the correct value. You may criticize this because there are some small differences. These small differences is because of the numerical errors between floating point number operations. Yeah, we can discuss this offline. But anyway, you may, if you measure the performance, you will see something very strange. This is not speed up. This is the total runtime. The single-threaded Julia code runs the fast. And with more and more CPU cores, you have more and more problem. The multi-threaded Julia code runs more and much slower. Yeah, why? Because there are lots of lines to read, but I can explain this very simply. Because for this atomic operation, those 64 threads, they must do this atomic operation in a serial manner, which means the operation must be done in order. This will serialize the entire calculation. That is why in the end of this multi-threaded Julia code, actually the calculation is done in a serial fashion. And what is even worse is because the thread manager need to schedule those out of order threads into in-order execution. That is why it will add huge overhead, which makes the multi-threaded Julia code much worse than the single-threaded Julia code. And here's the solution. I'm not going to dive into the details of this solution. You can copy-paste the code. I will just talk about high-level ideas so that without reading the Julia code, you know what is going on there. So what is going on there is to divide these 1 million terms into chunks, right? This n is 1 million, and then based on the number of threads, divide this 1 million terms into chunks, and then assign, and then go through each chunk, and then assign one single chunk to be a single task. A single task is here. This spawn this single task. And inside this single task, it will go through from the beginning of this chunk, CH means chunk, to the end of this chunk. And then only do the atomic operation after one chunk is done. And then to return the final result. Yeah, so basically you have 1 million numbers. You have, I don't know, 4 threads, and then divide this 1 million into 4 different chunks. And each thread or each task is going to calculate each chunk. In this way, there's no problem about out of order or in order calculation. And the synchronization only happens in the end to do the atomic add for different chunks. And then you will see that the calculation time reduces, except for the very last one. For the very last one, the reason is, as you can see, with 32 threads, the calculation time is really fast. But with more threads, it becomes slower because of the calculation is not enough to be efficiently parallelized among, let's say, 64 threads. But as you can see here, multi-threading is from the Julia syntax is very simple, just one synchronization, one spawn. But in order to have a good performance or correct result, it is very challenging. But no worries, if something that is not really clear, Alex and I, we are here. We can help you to clarify everything. And also for the speed up, as you can see, with less thread, the speed up is great. But with more thread, because of this problem, is not large enough to fully utilize 64 CPU cores, you have not great speed ups here. Okay, this is the end of the first way to parallelize Julia code. And then I would like to talk about the second way, using the so-called multi-threaded loop parallelization. The syntax is even simpler, just one macro, which is very easy to remember, add threads. For Julia code, normally you want to parallelize a for loop. In order to parallelize this for loop, you can simply put these add threads in front of this for loop, and then your task for multi-threaded Julia programming is done. However, this may not give you the best performance. Yeah, from the Julia syntax, it's very simple, but in reality, performance may be an issue. And also, you need to make sure that the execution for the calculation inside this for loop will be independent of each other. Yeah, I would like to go through this slightly quickly because time reasons. So in terms of Julia syntax, just put thread in front of this for loop. And then it is the responsibility of the Julia compiler to reduce this high-level multi-threaded programming to the real task-based multi-threaded programming. And there are ways to determine how to schedule those threads, but maybe let's skip those slides and just go to one case study, the so-called SAXPY operation. Yeah, because in my opinion, with a simple example, it's easier to learn or to understand what is going on there. So a SAXPY operation is a scalar vector multiplication and addition. The mathematical operation is very simple. Just the result vector y is a scalar. That is why here is S. Scalar multiply x, the input vector, and then plus the y vector itself, and then to generate the result vector y. And for the serial implementation, it's very simple. Just do the calculation for every element from 1 to n, and then the calculation is done. And here inbounds, yes, like Alex mentioned this morning, is to give the compiler some hints that this loop will never access some vector elements that is out of bound, so that the compiler can better optimize the Julia code. And for multi-threading, the task is very simple, just to make this for loop to be multi-threaded. To do this, you can just put these threads in front of this for loop, and then, so basically, your programming task is done. Here, this static is to just schedule the, let's say, the task and the threads in a static manner. And you may expect that with more and more threads, the performance, for example, in this case, measured by the so-called memory bandwidth, will increase with respect to the number of the threads or with respect to the number of the cores. But actually, the measured memory bandwidth does not scale. As you can see, this looks irregular. And what is the reason for it? To talk about the reason, we would like to talk about one, let's say, a difficult topic for non-computer scientists, the so-called ccNUMA architecture. So nowadays, as I talked about in the very beginning, one may have 100 CPU cores in a compute node. And in order to get the best result, to have the best performance, those multiprocessor machines use the so-called cache-coherent non-uniform memory access architecture, which means logically, the memory access for each core, they are transparent, but physically, they are different. Let's look at this figure. I think a figure tells 1,000 words. This is easier to understand. Let's say you have 4 CPU cores, and those 4 CPU cores, they have such a topology that the first CPU cores, they have their individual L1 cache, and they have their shared last level cache, and they have their independent, directly connected memory. And the benefit of such an architecture is with the increased number of the cores, as you can see, the memory access bandwidth will increase because they have their individual channels for each small group of cores, of those cores. Here, one small group of cores is 2. This is only for the purpose of demonstration. For real case, it's more complicated. I will show you later on. This is good to have a scalable memory access, but it is more difficult to run your application efficiently. And for Noctua 2, the situation is much more complicated. For example, it has 2 sockets, and those 2 sockets, they have different positions. And for one socket, it has CCD. This is a CCD, like you mentioned this morning. And for this CCD, it has 8 cores. Instead of, in my previous slide, 2 cores are grouped together. In the reality, for Noctua 2, as you can count, 8 cores are grouped together to form the so-called CCD. And those CCD, they have their individual, let's say, connections to those memories. From the programmer side of point of view, the access to those data in those memory, they are transparent, but physically they are connected differently. So that is why, for programmer, you may imagine the bandwidth will increase in a good manner, but in reality, it is not the case. And what is more complicated is there are multiple ways to configure, let's say, how those CPU cores are grouped together by setting the so-called NUMA domain per socket. For Noctua 2, there are different ways to configure the one CPU socket, and currently what is used is this configuration. This can be set in the so-called BIOS, basic input-output system. So basically, 2 CCDs, in total 16 CPU cores, are grouped together, and this is the so-called NUMA domain, non-uniform memory access domain. And then for one socket, which contains 64 CPU cores, it will have 4 NUMA domains. And in order to have the best performance for the software developers, a software developer need to write their code to match the hardware in a good way in order to have the best performance. Here, if one uses Julia to create the vectors in a naive manner, for example, just create those vectors by using random and then generate x and y and then launch this function. And then from software perspective, it's completely right. There's no problem. But from the hardware part, there are multiple questions because at the hardware level, there are multiple memory channels. So in which memory channel or in which part the so-called x vector, the vector x naive or the vector y naive will be stored. And then how about the execution of this function? This SAXPY function will be executed to access those different memory channels. And to solve the problem, there is the so-called first touch principle, so that the memory placement is determined by not at the allocation time, but by the first assignment to the values for those variables. And for example, here you have one single CPU socket, and it has 4 NUMA domains. In order to have the best performance, one need to think about to put the data, namely the vector x and y, into those NUMA domains in a correct manner. And for a naive initialization for x and y, if one just use random, and then the chance is high that x and y, they will be initialized or exist in this area of the memory. And if this is the case, and then only the thread 1 from core 1 will access this part of the memory efficiently. For the other cores, for example, for the other cores, if one has parallelized the code, for the other cores, they must go through this interconnect and so on, and then go through this part to access this region of data. And then this makes your code difficult because physically, this is a long way to go there. But from the software perspective, this is not a problem. To solve the problem, one needs to write the so-called NUMA-aware parallel initialization. And in this case, you can visualize the effect here. Instead of only locate X and Y in this part of the region, if one put the threads in front of the initialization for loop, and then this big chunk of the data will be parallelly located into different memory regions. And then if one start this parallelized multi-threaded SAXPY, and then the access to those data can be parallelized physically, not only in a software manner. And for Julia, one also need to do the so-called ping the Julia threads to the CPU cores. Because like I mentioned in the very beginning, the management of those threads is really messy. So one need to enable the Julia exclusive environment variable to make sure that, for example, the first Julia thread is pinged to the first CPU core, and the second Julia thread is pinged to the second CPU core, and so on. And then for the memory access is also follow this vertical line so that you will have the best memory access pattern. And yeah, this is a long way of correction. And as you can see, after those improvement, we can see with 4 threads, the improved bandwidth is 3.5. With 8 threads, the improved bandwidth is 4.4. It's a big improvement over the previous one. But another observation is you will reach the saturated memory bandwidth, which is possible. I mean, possible means physically possible from the hardware very quickly. With more and more cores, there's no improvement because, with 16 threads or maybe 8 threads, you can saturate the entire memory bandwidth for the CPU socket already. And yeah, this is a deeper, let's say, question for computer scientists, why there is a small drop of the performance with 16 CPU threads because of the contention for the so-called NUMA domains. But this is, let's say, very picky for the very last bandwidth for the bandwidth measurement. You can forget it. And yeah, because of the time reason, I would like to skip those thread ping package. Basically, this is the package so that you can ping your threads to the CPU cores like this to ping those threads to the CPU cores to have a good performance for your multi-threaded code. And those are the screenshots, yes, of course, made by Professor Plazer on Noctua 2 system. And those are examples you can also try during the hands-on part. And as you can see, the SAXPY is just a multiply and add calculation, but it is not really easy to achieve the best performance. The best performance, the hardware limit is 200 gigabyte. And by using Julia with 8 threads and also thread ping NUMA domain, lots of technical details, in the end, we can achieve 170 gigabyte, which is already very fantastic. Okay, there are some best practices for optimizing memory access for NUMA domains, but I would like to skip this part because this is more deep. But anyway, if you found this topic interesting, we can talk individually, because I don't think this is a very easy topic for non-computer scientists. And summary, Julia support 2 ways to do multi-threading. And in this part, we mainly focused on the first way to do multi-threading, the so-called task-based multi-threading. And we went through the so-called loop parallelization very quickly. As you can see, for multi-threaded Julia code, there are only 3 macros. The first macro is to do the synchronization. The second macro is to spawn your task. And for loop parallelization, you will have the third macro, which is add threads. From the Julia syntax, it's very simple. But as you can see, I talked about it for a while. There are many chances that you may have incorrect result because of the so-called race conditions, or maybe you have performance problems because of the so-called ccNUMA architecture, or cache coherence problem, or even false sharing. But those topics are really, let's say, specific for the programmer who really want to get the best performance, get the very last drop from the CPU power. And therefore, those topics are not included in this course. And, that's all for this part. So for the parallelization in one single compute node. And tomorrow, Alex will talk about the distributed computing so that you can move beyond one single compute node to utilize the entire cluster system to run your calculation. And I think one question in your head is, okay, for one single compute node, there are enough problems, right? The NUMA domains, false sharing, there are huge of problems already. But if we move to MPI to utilize the entire cluster, there may be even more, 10 times problems, and so on. I would like to say no. No, with MPI, there's no NUMA problem. With MPI, there's no NUMA problem. With MPI, there's no false sharing. That is why I just talk about this very quickly. Personally, I'm not really a fan of multi-threading. I like MPI more. So I think MPI is the way that you need to go for really HPC, for real parallelization, because it's, in my opinion, simple than multi-threading and has less problems with hardware. Yeah, let's looking forward for Alex's talk tomorrow. Yeah, that's all. Yeah, the contents, as you can see, are from Professor Christian Plez's lecture, targeted for real computer scientists. Those NUMA domain problem, false sharing. But in my opinion, those are not really important for most of you, especially if you want to use MPI. Those problems gone automatically. Okay, that's it. Any questions from your side? Except, yes. 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 You can mix multi-threading and MPI together. If you do it in the correct way, which is very challenging, you will have the best performance. But normally, the normal situation, even for me in some case, if I mix multi-threading and MPI together, the performance becomes even worse. Because this is not really like a simple, okay, let's mix MPI and multi-threading together, we have the best of the best. No, normally you have the worst of the worst. Really, I'm not kidding. MPI is really, in my opinion, is really the the choice. It's really the choice, not really multi-threading. Yeah, I really like MPI because with MPI there's no NUMA problem, because the allocation of the memory is always local to the NUMA domain. You needn't to think about, okay, there is a NUMA domain. Okay, there is whatever the so-called different connection of the memory channel. You can forget about everything because the process will do this automatically for you. Yeah. Okay. Any other questions? Or yes, please.
Every single combination. How to multiply, which method to use, what would be the best?
You can, I would like to recommend you to use this threads, in terms of the simplicity of the Julia syntax, I would like to recommend you to use this threads. But in reality, is this really a pairwise matrix operation? Is this really the case for your work? I recommend you to use GPU. Yeah, because GPU is much faster for bandwidth. I can clarify this afterwards. Yeah, and by using GPU, it's much simpler than this than this case. And for using GPU, there's no NUMA problem. As you can see, I'm a hater of NUMA. GPU, there's no NUMA problem. That is why you can forget about those NUMA domains, those CPU core belongs to this CCD or so on. There's no such a problem. Yeah. Yeah, but we can talk later about this matrix calculation.
Python or with Julia on GPUs?
Yes, this is a good question. Yes, someone may think, okay, this is a problem of Julia. No, this is not a problem of Julia. This is the problem from the architecture, from the hardware architecture. As long as you use those or the chip designer, I mean CPU designer, design CPU like this is a limitation. No way to get rid of this NUMA problem or whatever. No way. C, C++, Fortran, whatever. The problem is at the hardware level. And because I think most of you are not really computer scientists, so that is why I do not want to confuse you. I think you are already confused with this strange NUMA thing. Forget it. We are looking forward to MPI. With MPI, you can forget about everything. You can forget about those NUMA problems. Yeah. There's no problem. It is solved automatically, right, Alex? It is solved from the beginning. You never see this problem, NUMA, with MPI. And also for MPI, normally there's no race condition. You know, we talk about this thread is competing with this thread. This thread is competing. You know, this is like fight. You know, this is really very bad, not nice. For using MPI, normally there's no race condition. You can forget about race condition. So that is why we are looking forward to you tomorrow. Yeah, but anyway, if there's something that is not clear about NUMA or race condition, feel free, we can chat individually, but not at a larger round, because this is really confusing. Yeah. Okay, I think that's all. Okay, let's take a break. Yeah, thank you very much.